So we have this problem, which is the failure probability of a mechanical device, and for which we have the exponential distribution function. Probability density function is given as 3 e raised to the power minus 3t. So let's develop the data. So here by inspection we can recognize that the lambda value is 3. So that's the fair thing. And so let's define the time scale. So we can consider that for this device, for example, the time is in, say, hours, right? Okay, years, right? And then I plot here f of t, the density function. So I take the values 0, and then I take the value equals 0 plus 0.04. So the time period has been considered very small as compared to the year, right? So I can plot here the density function. So density function is the value of lambda. So lambda value is at $1. Asterisk e raised to the power minus lambda $1 times t. So the first value is 3. And then we can keep on. For higher time intervals. Okay. So these are the values, right? Now, this value is also possible with Microsoft Excel. So I write here how to compute from Microsoft Excel. So this value is governed by the exponential distribution. So I write exponential dot distribution. Function is available in Excel, Microsoft Excel, and see how it works. It requires the value of x, lambda, and the third one, cumulative or the density function, right? So it means exponential distribution requires only one parameter to be known from experimental data. So 0, lambda value I can get from the cell, and this is the density function. So you can see the nomenclature. True for cumulative distribution and false for probability density function. So I'm looking here for the density function. So with the false, this will be fine. False. Okay. It means the calculations are correct. That's fine, right? So we have correct calculations. It means now I can further go for the other estimates. So this is the test. F of t from the function and f of t by the Excel given function. So they are identical. It means we can also develop something like Microsoft Excel. So that's the confidence we would like to give to our students. Now I compute f of t. So I can compute it either by the original function. F of t is the failure probability. Failure probability up to this point, right? So I'm going to write here from Excel function. Okay, that is fine. Well, I prefer my own function. 1 minus e raised to the power minus lambda, which is at $1 times t. So that's the probability, exponential probability. I got 0 value. The f of t has a property that it saturates at 1, right? Cumulative probability always saturate at 1. So we have got to 95%, right? So 95% of the equipment of the components of, say, bulbs of that company having this lambda value, they will fail in within 1 year, right? So that's the interpretation. So just to see that clearly, let's extend our calculations to unit 1, right? Okay, so 98%, right? They will go up to 1.5 year, right? So if you have started testing this cumulative distribution, if I develop the cumulative frequency distribution, CFD, cumulative frequency distribution, something like if I started the experiment with 500 components, so what will happen? So I can only say that this probability times 500. So no component will fail at the moment you start it, right? Every component will fail when you start its operation. So out of 500, how it goes? So you will find that the with this distribution, first 56 components, right? Since the components cannot be fractional, therefore to give you a bit realistic, I set it round to 0. Is the components are integer components. You cannot have a half component. Half component failed, half components working. If you are talking about one component, that's not going to be the case. So it says that with this distribution, we'll have first 56, not first, random 57 out of 500 fail within first interval. Then within from this to this one, you have further components failed, and then you have further components failed, right? So 107 components will be failed up to 0.08 years, right? Let's develop the lambda value. Where is that lambda value? Lambda value is the failure rate, right? Number of components failing from the original quantity. Let's see how we calculate that. So if I count the number of failed components in interval, failed in time. So how many components failed from 0 to 0.4? So this is the number. This is the number 57 minus 0, right? This is fine. These are the components that has failed within this interval. For the next, how many components have failed? So you have in every interval, you will find that at earlier, more components failed in the first interval than second interval. And this was the data that you collected in terms of frequency distribution from the experimental point of view. These are the components in failed. Let's see the time distribution of components in survival, right? Surviving components. Surviving components. Surviving components. Surviving components. So at the beginning, you had all 500 components, right? Is it fine? So I can write here that the number is 500 minus the failed components, right? Total failed components. Total failed components. So in the first interval, 57 were lost. In the next one, 50 more were lost, and it went on. And finally, you will be having very, very small number, right? Is it fine? So 493 failed and 7 survived. So it's a fair number. Now, if I compute the probability, how many components failed out of actual? And of course, it is bound with some interval, right? So let's see what is that number. What is that number? So this is the critical part that is going to define the failure rate, reliability attributes. failure rate. So I will, of course, compute after some time interval. So at this interval, number of components failed out of total, right? That is going to give us the probability of being failed. So how many components failed in the first interval? 87. And out of how many they have failed? They have failed out of 500. So that is the probability of failure. Like number of, in total number of trials, how many times you got the head, right? And times I multiplied with the time interval in concern, right? This problem we have considered equal time interval, right? So you may have that interval changed. So I write the journal expression. How was the time interval? So minus 0. Wow. The number is 2.85. And here we go. If I perform this calculation again and again, so you will find most of the time the number is 2.7333. So the number, if you round it, for most of the cases, it is rounded to this number. This is rounded to the lambda value. That's why this is known as failure rate. That's why this is known as the failure rate. So we define the failure rate. This is the lambda value. So of course, from actual data, from experimental data, and from the model, there are differences. You know that I have compromised. I have rounded this one, right? So I have lost already the fraction. I compromised the fraction value. Therefore, we have found a bit mismatch between the value, right? The number of components surviving, the number of components failed, and we have the cumulative frequency distribution. Here we define a new function, which is in terms of probability, not in terms of components. We call it the reliability function, R of t, and you have the failure function. So the complement of failure function, f of t, is the reliability function. So reliability function is the normalization of surviving components. So I can compute it directly as it is equal to 1 minus f of t. 1 minus f of t. So it will be the normalized one. Like if you calculate the parameters, the functions, without defining the total number of components, right? So it's a normalized one. Is the is complement of f of t. So if you add f of t plus r of t, they are equal to 1. This is something we found, that if you perform the analysis in success domain to compute the performance of a system, so 1 minus that one will give you the failure of the component, right? So this is something we study in the success-free structures and failure-free structures. So two approaches in engineering to discuss the performance of a system and the failure of the system. So this is very nice. You can develop the graphs of between the parameters time versus f of t. It is the probability density function. Time versus f of t. This is the function of f of t versus time. It is the failure distribution. R of t versus time. This is the reliability function. And the failure rate is also said as it is also known as the hazard rate. This is the governing parameter for exponential distribution.